mic is picking up the audio from my MacBook speakers, and that's how you hear coming through. But if it works, it works.
Okay, and I don't hear myself anymore, so I guess that also means it works, because that was crazy. Okay, so does it work now? Can we start talking? Should we?
Yeah, I think let's talk. If it is, yeah, I think let's just start.
Yeah.
Yeah.
Okay. Okay. So I was saying, apparently no one here heard me, that I started here with creating this repository. Where we are starting off now when we are picking up the Sieve. Okay, you need to talk to me, Daniel.
Oh yeah, cool. So the link for this repo is in the description, by the way.
Say again?
I added the link for this repo in the description.
Awesome, that's why I pasted it to you. So that's super. So this is the project in the repository. It has some setting up of the tools we're going to use, and it has this starting closure file where I pasted where we like a bit left off the last time when we created this Sieve together using closure sets. So we should probably start with starting the repo here. So, and I choose these three aliases. Benchmarking for the benchmarking stuff. If we get to the compiling stuff, it's that one's good to have, and the profiler is also good to have. I don't know how much we will be able to cover here, but anyway, all those. The repo should be with us in a moment. There it is.
Right.
And as always with Calva, and I actually think I now know how to fix that, but until I fix it, always start with loading the file. Then Calva starts working.
Cool.
And yeah, so here we have the last Sieve. The one we made in the last episode of On the Code Again. And we were using sets. And should we like reiterate the Sieve algorithm a bit here maybe? So the algorithm is a way to calculate or find prime numbers up to a certain number. And some old Greek dude figured it out that if you would just start with the first prime number and then remove all its multiples, then you were like on your way to the rest are like candidates to be in primes. And then you move forward in the number array until you find something that you haven't removed yet. That will be also a prime, and then you remove all the multiples of that one, and then you repeat this until you have like walk through the array, and then you will have removed all the primes. It's a genius thing, I guess. But otherwise, what you easily end up doing when you're trying to find primes is just like trying if they are divisible by something else than one and themselves, right? And that gets very inefficient if you do that with every number. So this is what this reduce thing does. I would credit Daniel for coming up with it this fast.
Ingenious solution.
Yeah, so we are here making ranges of all the multiples. So we're like reducing over the numbers. That's we start here from 2 and up, and we are reducing over those numbers, and all the multiples gets into this set, and then we use set difference to the accumulator with these multiples, and that will remove them. And until we're over the limit, and then we will have reduced the numbers. So that's how this one works. So if you would test.
Sorry, just a quick note on that limit. So that limit is the square root of the input. So if your input is 100, the square root of that input is the last number that could conceivably have multiples.
Yeah, exactly. I don't know if this Eratosthenes dude figured that out, but someone has figured that out. That you don't need to, when you have reached the square root of the limit, then you can stop. Then you have sieved everything. So that's a very good point here. So this one should then return an empty set, right? If we do it with a zip1 here. So that's, we're passing that test. And this one should only return 2. This one should only return 2 and 3. And here we should get 2, 3, 5, 7. And we do. We have here in this file some sanity check numbers. So for thousands, you should have 168 primes. And for 100, those are 100 sets. But we can check that we have the correct count. That's 25, and that's what this table says. So it could be right. And then we could try to, if we sieve up to 1 million here, so we could do the count of that. It should give us this number, 78,498, and that's correct. So we have a correct implementation of the sieve. And if we run that with time, we'll see how fast. Do you see the bottom of my screen here?
Yeah, I can see. So it takes 3 seconds to run.
So this one takes 3 seconds to run if we use count on it. But as we also touched last time, time is very, just running it once, you know, the JVM is not warm and everything, a lot of things can go on the computer at the same time. This is a laptop computer, right? So, I'm telling you, yeah, everything can go on. So what you do, you use this Criterium benchmark tool, or I think most people use that because it's very well built and well thought through for someone who knows the problem domain has done this. So we'll require that one, and then we will quick bench this and see to get like a more accurate number on how fast this is. So
just my understanding of Criterium is basically it does the same calculation over and over again. So it repeats it on the same. It repeats running the
yeah. That is correct. I don't know. I don't know what's happening because we don't get an answer back here. But I'll give it some more time. While waiting for that one, it does it all over and over again. And this quick bench does it not as many times as if you would use bench on it. But right now it takes so much time. I'm not sure what's going on here.
Oh, there we go. It just. Oh, did you cancel it?
No, I interrupted it. Cancelled it. So we could time it, but when we try to, we can. Require it, and then if we run it, do it one more time. I should run it actually with this with progress reporting on.
Okay, now give us some feedback as to what's
exactly. I'll interrupt that again and we'll see if get any feedback with progress reporting. Now we get feedback, warming up. We are not running it with more than 1 million, right? No.
No, it looks.
And it does more. It does more than just run it. It makes sure that the just-in-time compiler has done everything. There's quite a lot going on actually in this tool, more than just running it many times. And if you're curious about that, I can recommend a talk by the guy who made this closure goes fast blog. We should add a link to that as well in the description.
Yeah.
And he touches there a bit about what's going on here in the QuickBench. For some reason, QuickBench didn't work for us, but with progress reporting, it did.
It did. Yeah.
So it says that the execution time mean here is 3 seconds, and you can see that the standard deviation is pretty. So you will get results if you just use time, even if you do it many times and get it just in time compiled and stuff like that, we still get a lot of variance on it. But this is we're just using QuickBench, of course. But anyway, this is a much better measurement on a hand. So that is what we want to try to improve. And here we're using a set, but one other data structure enclosure you can use is the vector. And if you imagine that you have a vector and you fill that vector with truth, so you have like 1 million booleans in that vector and say true for all of them, and then we start sieving, we will set them to false as we are removing numbers from the sieve. So that is like one way to do it, and you can do this, of course, from map and filter and reduce, and yeah, a lot of. But I'm thinking we can set this up with loop.
Okay.
Because that just makes sense. So we define ourselves a sieve. Let's call it sieve vector, and it will take a number. We can have it something like that, and we can start with, I guess, checking if n is less than 2, and in that case we just return something empty, like we had in the when we try this sieve here. Is that right?
Yeah, because we only numbers above 2 are primes.
Yeah, and otherwise we will return something else. So let's say we have I will call them primes, and that's a vector of truth, as we said, right? So we repeat n times and true.
So now there's a vector with of the length of the input all the values are true.
Exactly. So if we do a rich comment here, let's do one here. And we do, I think it's a factory. repeat 7 and true. That should give us true 7 times. So we convert that to a vector. So we have a vector of that. So that's our primes that we will sieve through. And if we want to test this, let me copy this structure. Here. We can remove this for now. And like that. So if we do this, we will need to compile this first, and we get an empty vector, and for that we get 1 past the closure vector. Repeat.
Wrong number of args.
Okay. So it's okay. That it should be. If we save that, we get 2 true. Yeah. So that's a start. It's a wrong answer, but it's on its way. And then we can. So we don't want to return the primes here. We want to return something else, and we will loop, as we said, right?
Yeah.
So if we loop with p starting at 2, say, and of course, if you would start with p1 and then take all multiples, then we would be, you see, then we would have just false in the vector, and that would be the wrong answer. So we need to start with 2, right? And we will then also need the primes here, because we're working with a mutable vector, so we need to loop back the vector all the time, because we're not mutating it, we're just making a copy. So we need a new copy every time, start the loop, right?
Okay.
Let me know if that doesn't make sense.
So you're looping. In closure, the loop can take as many. So you basically bound 2 to p, primes to primes, and then you can recur the loop and rebind those with the recur.
Thank you. Awesome. Exactly that. While p is less than 1, we should do so, right? And then if we remember when we said to the Sieve, we will try to find the next thing we haven't removed yet, right? So that is if we index this vector with p, and that is true, then we should do something, right? So now we want to recur the loop. So we recur with p being something next p, and we then that's going to be bound here, so it's going to be 3 next time, right?
Yeah. And
now the next primes is what we want to do. So that will also be a loop, and in that one we go from let's call it I for index, and we go from the next p. We don't want to remove p, right? Because that is a prime. We want to start with the next p. So if we do it like this, that should work. And sorry, yeah, primes is primes, and then now in this we will loop over I as long as that is less than n. We're not doing the square root thing yet here, but we will get there. And now we want to recur with the next p. So that this is this equivalent to this here, where we use the range to do this. Here we do it like this. Is just we loop, and always with the next multiple of p. And that's the, but for primes, we want to return something new, right? So it's we associate then on primes on the index I, and then we associate false here. So we have created all of them true. Now we will associate false for every multiple.
So let me just get this straight. So you're recurring, but the argument for, so there's the first loop, you recur it, and then you pass through the next p, which would be the next item in the list, and then the primes that you pass to that, you create another loop, and then in this loop you want to remove all the multiples. That's what this current loop is doing, is removing the multiples.
Yeah, the innermost loop is doing that, exactly.
Yeah, and so I just see the recur is spelled, just needs to get rid of the e on the end of the recur.
Yeah, that's my English. So, and if we then our past then we shouldn't recur. Then we should return the primes. Now we need to this if here also needs to do something, right? And that one should recur. So this is in the case where we are on a prime. This one returns true, that's a prime. Then we should also inc p, and yes, it has to do that, and we should just give it the primes that we got in there.
So this case is you're not on a prime, isn't it? So if nth primes p means that the value is...
Yeah, exactly.
Okay.
Yeah, we're not on a prime. So let's see what we're not on a prime, so we should maybe if you try to summarize it, it makes sense.
I don't know if I can do that. Let's just the first loop. Let's just start there. The first loop is if the current index is less than n, then you want to check if the current index that from your primes array is set to true. If it's set to true, then it is a prime.
Yeah, exactly. Then we need to sieve, right? Exactly.
Yeah, and then we do the sieve.
And if it isn't a prime, we can start sieving or removing multiples of that, because that would be crazy. Yeah, so that's this. And when we have reached the end of the array or the limit, we return the primes. In theory, this should work as it compiled at least. And then if we try it with that one, of course, this gives that. Okay, that's wrong. This gives that. It's also wrong. Here we're starting to see some faults. I think that we also need to like remove the first two ones from here. So if you can do this with a thread or something like that, but I will just associate some primes, false, and the index 2 also as false. So if we do like that instead.
Okay, so now automatically they're false. Yeah.
Is that correct?
Well, that I'm assuming is that 0 and 1. 0.
Yeah.
0.
So,
yeah.
So what we need now is something to we shouldn't return primes really here. We should return like the prime sequence. That will make more sense. But this started to look correct. So, anyways, but if we take the primes and we say we map this function an index and then the value, and we say that when the value is true, we return the index. Okay?
Cool.
And this now expects two arguments, right? So primes will be the last argument here. If you look here now over here, it will say we're only calling it with one argument. So map takes several arguments. So we want to give it the count of primes, the length of that vector. So that will now be bound to I, and primes will be, next prime will be bound to V in this case, right?
Could you also use, sorry to interrupt, but could you also use map indexed here?
Yes, we can use map index. But let's just finish
sorry.
this one first then. Then we will remove the knees from this one. So if we do that, then we should get 2 there. Okay. So there's something here.
Oh. That was the symbol.
No, still. Yeah. Something like that. Something like that. 2, 3, 5, 7. That's correct.
It's 2.
That's not correct.
Oh yeah, 3 is a prime.
We have some bug here. What would that be?
What are those primes? Is it ending on 3, or is when we set the input to 3, we're only getting 2 items in the vector back?
Yeah, so maybe that's what's going on here. If we go until it's equal, then like that, and would that work?
No.
Okay,
that's out of bounds.
We need a bigger vector. That's better.
Cool.
So we should have 25 there, and we should have. Yeah, that's great.
Yeah, it's far more performant.
Faster, right?
Yeah, much faster. Jeez.
I don't know if we're like taking notes here, but we started with 3 seconds. Now this one is down on less than a second. So that's good. But we could, as we said before, with Criterium, we will get a more accurate number for it. So let's do it like that.
Okay, cool.
Yeah.
Yeah. Jeez.
So it's 0.7 seconds I guess that's good. You said that we could use map indexed here instead.
Yeah,
So
I'm
let's
assuming
do
it's
that.
slower.
then we get it complain here that we're sending it to, right? So we shouldn't send it this one.
Yeah.
And then I'm just doing a sanity check it. Yeah, that's correct. And now when you see this pattern, you map index and then you remove. Then there is something even, you can instead use keep index because that's exactly what that does.
Oh,
so
okay.
if you do that, save the vector.
And performance-wise, is
So
there any
keep index.
difference?
I guess it's a bit better performance-wise, but it's if we look at this now, performance-wise, when you read it, at least it's much less to parse, right? You don't threading and mapping and removing. You just say keep index, and then you have that. So, oops.
Valid symbol.
Okay, sorry. Yeah, so keep index and map and all of, when they don't have an argument, they return a transducer. We're not going into transducers here, but that's what happened now. So we got back a function because I had forgotten to feed when I wanted to show you just how efficient this was reading.
Yeah.
I forgot to give it the things it should keep.
Okay.
So there you have it.
Cool.
So that is an improvement from when we were map range and removing. Yeah. So let's now I just think a bit about the rules for this competition. They are a bit special for this drag racing competition that David Plummer set up. So he allows for us to return the sieve. We can either return the prime numbers as we're doing now, but we can also just return the sieves if we like. And in our case, since we want to be as fast as possible, we are going to utilize that part of the rule set. So then we can take this and we define a function for, and I call it looting. So I will call this loot. And it will take the primes, and so we have a function for doing that. And then we can return just the primes in this one. And then we have our loot. And then if we just do this here now, we will return the sieve. And that's okay by the rules. And if we then want to, we will need to loot it.
Cool.
So let's do that for all of these.
Here.
Here we're moving into a limitation of Calva parity. This is not multi-cursor, so this is a bit tedious to do. I wish it was, then we could do multi-cursor and slurp them all. I don't know how to fix that actually. It's but now if we loop this, it's the right thing. If we count this, we will of course get this ink n we have up here. But then we count the looting method, that is 25. But now we can time here. Right? I shouldn't be timing this because that will try to print out
the vector.
A million things. So that's Calva won't like that either. I don't know who would. So we will do it like this instead, just to see. how fast it's going. So now, since we're not doing this work in the Sieve, we are a bit faster here.
Cool.
So let's see how much faster we are. Now we shouldn't count. But we can time count the loop. Let's see, so we have the right answer. We still have the right answer. That's good. And now I think we don't need to count there. We just quick bench this vector. There is nothing lazy going. Why I'm saying that? Because if we had like returned lazy sequences for this, and we're using Criterium to see how fast that is, then a lot of the work wouldn't have been done. But this is a loop, so it's eager. It will. Did that make sense?
Yeah. So if you turn a lazy sequence, the values don't get realized, so no computation is done, and Criterium obviously won't.
So when I have been doing this thing, that's not that. Oh, that is so fast.
Yeah, 0 seconds.
And then I realized I have been like not doing the work. So this is where we are at now. So we have improved. I guess the basic algorithm. Now we could try to see this square root thing. How far that one will take us, right?
Yeah. So okay. So essentially,
we say we have the. Sorry.
Yeah, I'm sorry. You carry on. I was going to say I think the same thing you were going to say.
Yeah. So as we remember from this one, we took advantage of the mathematical fact that we can stop the sieving at the square root of n. And so let's make that clear. Square root of n is it's math square root n. This is a floating point, and we will probably know have that's a quick setting, yeah. So the ceiling, it should round it up, right?
Yeah.
So now we have square root of n, and then we add here. So we're going to until we're at square root n, square root n.
I think sealed is as EI. Yeah.
Like that?
Yeah.
And then we should just make sure that we still have the right numbers. We do. And if we then time to 1 million, it looks faster. But let's do it with Criterium. There's a lot of Criterium runs when you do this. And this with progress report, yeah, we're much faster, right?
Yeah, really.
That was good.
Okay, but that makes sense though. I mean, we stopped half the execution.
Say again?
That makes sense though, because we've cut out half the execution, basically. More than half.
Yeah, much more than half, I think. Yes, we did. There is one more thing you can do, and it's actually that we are starting this loop at the first multiple of p, and similar to the square root of n here, we actually can start the loop at the square of p. So let's say we have, then all the even numbers are gone, and then we find 3. The first multiple of 3 is 6. That would already have been removed.
Oh wow,
But
I didn't know
9
that.
wouldn't. So we can start at 9, and I have like just tried to go those through my head, and it works. I just trust it, because it's not obvious to me why it is. But it's the same with this here, right? This is some mathy person that has figured this out. So you should be able to start at the square of p every time.
Okay, so we're just limiting the range of we're starting later and we're ending earlier.
Exactly. Yeah. So we're only doing the work we need to do as far as this algorithm has been optimized. We're still doing the right stuff here. So we can see that, okay, this takes, it looks slower, but if we do this with Criterium.
But I suppose that goes to show you, that time is just same kind of.
Okay, but it still seems like we didn't win a lot. By it looks similar in the results. I'm a bit surprised because that's not what I have seen when I've done this before. It's a bit, but that's what it is. Maybe this is. Maybe this is compiled to some more inefficient code than the plus was. That could be. So it's doing some funny stuff when it multiples. That could be. But anyway, we can, with our logic, just realize what you just said. If we're starting later and ending earlier, it should be less work. So we shouldn't do that work now that when we know we don't need to do it, right? That's so let's leave that optimization in, I would say. Then the next thing about this competition, but also if we think about the Sieve, the work we do when we Sieve, is that we're removing all these even numbers. That's the first thing we do. And you can imagine that doing this on an immutable vector is a bit expensive. Right? It creates a new copy, lots of sharing going on. It's efficient, it still work. So if we wouldn't do that, start with doing that 500,000 times. That would skip a lot of that work. So that should go faster. So if we just use like half the Sieve. Do you follow me?
Yeah, you're saying that when we create either immutable data, even though the data is shared in the memory, it's the connections are what take a lot of space.
Yeah, it doesn't really matter. Yeah, that it is immutable is certainly a factor here. But regardless what data structure you use, updating it will cost. That's where you pay, right? So if you know that updating this first thing you do, you update 500,000 even numbers.
Oh,
so
okay.
That takes time.
I see what you're saying. Half the size of the data structure.
The rules for this competition that David Plummer has set up, then he allows us to return a Sieve containing only the odd numbers.
Okay.
So, because there are other, it's called wheels. I mean, if you look at the Wikipedia for the autonomous algorithm, there are like optimizations on it called wheels, and I'm not sure if this is the first wheel. Could be. I haven't really looks that up. But anyway, you have a crib sheet that you apply first. But all the even numbers are gone when you start. Then this should go faster and be within the root this drag racing competition.
Okay.
So I suggest we do that as the next step here. Just take advantage of that. That part of the rule. I will just copy this. For now, just paste it as the same name. We have a complaint here about reusing the name. But anyway, so now we know that we have something called, let's say, half-n. You know? And that is n divided by 2. And since all the even numbers are gone, it's a bit special because we want 2 still in there, right? The 2 is both a prime and an even number. It's just the only even prime.
Yeah.
So it's probably wrong to set anything to false here in the start of this vector, because it will start with 1 and the next one will be 3, so we will not have. So let's say we treat the first index as the 2. So then it is correct that it is true.
Okay.
We can play that word. And then we should, let's see, we should, okay, it would be like this, right? Only now, if it is this 1 million vector, 1 million long vector, we just have 500,000 and 1 in this case. And then we still stop at square root n, because that hasn't changed. But now we need to index this vector differently. So we shouldn't index it on p, we should index it on half p. And we should not just ink p, we should increase it by 2. And same here, we should loop from the square of p divided by 2. And we should stop at half-n. And then when we recur here, p should do that. So I think this should be correct. And if we then loop this Sieve, it says, so this is wrong answer. That is also the wrong answer. It looks a bit right, but I think it's our loot function here.
Yeah,
that shouldn't return. It shouldn't return ei. It should return that times 2. So if we now look at this, it's wrong for the first one. That should be should probably ink this. And now we have 1 and 3 there. That's wrong. That's wrong. 1, 3, 7, 11. So what's going on here? We have this. We said that we should treat the first index special, right?
Yeah, it should be.
So if v is 0, no, if I is 0,
they return 2.
We should return 2. Else we should return that. That should be better. That says 2 and 3. That says 2 and 3. 2, 3, 7, 11. It should be. Where is the 5? So that is strange, I would say.
Is that an issue?
Are we going? We went like to. We didn't. But before we just start, we inked this, right? Because we weren't listing the end of the sieve. Is that the problem? That we're now doing where we shooting? But then where is the 5?
Yeah, it's weird that the 5 is the first, but that's the first. No, it's the second one. So 2 is returned, and 3 is right. Then it must be. So it's like true.
Okay, so we shouldn't start on. We should start on 3. Because here we just say 2. Execution error. Key must be an integer. And that is on line 85. So here,
Search.
I is integer. So we should probably, this is returning some floating point maybe. So we could convert that to an integer. So if we look at the int here, it coerces to an int, right?
Okay.
So it will, yeah, whatever you feel. So that should, what that was on the 10, right?
Yeah.
Yeah.
Okay. So it was trying to associate a value to primes at an index which was a floating point, and it just didn't work.
Exactly.
Yeah.
So we should, but I'm a bit confused now why we have where the 5 is. That's so strange.
It wasn't that because the associate would have broken before.
Say again?
I'm just trying to think. The associate would have broken beforehand as well. It's like it didn't get into this loop with a 5.
Yeah, you're thinking, yeah. But now it did, right? Now we are entering with something odd there. Now we have the 5.
Yeah.
Sorry, we have the 5. We're shooting here. And so that's correct, right?
Yeah.
That's not correct. Also overshooting. Okay, so maybe we shouldn't go lazy. That was not the
Is it not the initial vector? Could we do not yeah.
We have a shorter vector.
No, but
Now
now
we get that wrong instead.
no, but then it
To
should
get the right thing here. Yeah, we should probably think a bit. So.
and that if p is that's fine, is less than or equal to square root n.
We repeat.
Oh, is it not the indexing? When
Say again?
is it not the looting? When we that loot function? When oh no, because that still would be if v is.
So this one. Oh, that one should be the same, right?
Yeah, that's.
Then we should have. Okay, we haven't.
No, that should be the same because it's the primes that are getting returned.
That's correct, and that's.
No, that's also overshooting.
Correct, right. I think we have 26. So we're just.
It's just
is
one.
It correct? Otherwise, it is right.
No, because this one Sieve vector 100. It should stop at 100. And it's going to 101.
Exactly. It's going to 1. Here we're going while we're less than half n. And that's correct. It was correct before at least. Mm-hmm. But I was a bit confused that. So we're doing it like that. And we do that one, we get 2. So here we're like, for this case,
3.
We're missing.
Yeah, it's just that case, yeah.
We're missing 3. And do you have any watchers on the stream?
We have 4 people watching. If
so any one of them have any idea what thinking wrong here? And that would be.
If any of you guys know what is wrong here, please comment.
So I will remove that one as well. I don't think that's actually.
Now we got 5 watches. More people are trying to help us.
So we're looping.
If n is less than 2, return. If n is, no, it's not that.
I'm going to move this because it's going to be easier for me to read it like this. I think we don't need to.
Yeah, we don't need to clear the primes again.
Like that. It won't change anything, or I would be a bit surprised if it did. Yeah. So we're still wrong on this one, and we're probably wrong on this one as well, right? It's when we end on a prime, that one is not included.
Could you? Okay, so I'm just asking if we could repeat what the problem is. So the issue that we're having now with the Sieve.
So
again.
Yeah, please continue.
Oh, okay, sorry. So the issue that we're having now with the Sieve is that when we pass through an input and the input itself is a prime number, it's not being included in the output of the Sieve. So if we Sieve vector 5, 5 should be included, but it's not. If we Sieve vector 3, 3 should be included, but it's not. So we're just trying to figure out where it's exiting, or where it's not looping.
Yeah, so we're missing. We're missing the last one. Should we just now? Since we're almost correct, and we're certainly correct for 1 million because that's an even number. We can at least see if it's worth it. I mean, this optimization. Does that make sense?
Yeah, we can still check.
Time this, it goes much faster, and it does the right thing for 1 million right now, and yeah, so we're down in 150 milliseconds now.
Yeah, so that's a lot faster.
So this problem well, actually, we are competing in this drag racing that the programmer set up, then it's worth solving this mystery, because it is a mystery to me. I don't see why this could it be. I'm wondering if I'm just trying this.
If it's the Sieve.
This something happened with that. Couldn't change the logic.
No, but that should still be fine. Doesn't it?
Say again?
Why is so Martin's asking why is P set to 3, and that's because we're skipping the case of 1 and 2 because they are not primes. They're automatically false.
2 is a prime.
But 2 is a special case.
We know that already, and it's removed from this, not present in this array because all the even numbers are gone.
Yeah, sorry, I meant like 0 and 1 because we're starting at 0.
Yeah.
Wait, and I'm gonna need to get back to work soon.
Cool. So maybe we should pick up this up like next Wednesday or something like that, or?
Yeah, I think that's. We just carry on from here.
I guess that your viewers on the channel will have to let us know if they think this is worth watching. But if they do, I think it would be fun to both try to solve this strange bug, of course, but then also continue with because now we are not mutating the vector, we are using an immutable vector, and we just can't imagine that is less efficient than if we would allow ourselves to mutate. And there is a mechanism that we touched last time, the transient vector. So that's a mutable version of each of these immutable data structures closure.
Yeah.
So that will let you inside like the loop, you can mutate it, and then at the end of it, you would just like make a persistent thing of it, or the persistent means the mutable ones. So that would be fun to see how much faster this goes if we use transients, and then it would also be fun to see how much faster we can do if we use Java bit set or Boolean arrays and stuff like that. I know that they are faster, but I think it could be interesting to see the progress.
Yeah, I think we'll carry. I think we must just do that. Carry on with the progress of this. We'll fix the bug next week, and then we'll look at transients next week, and then in the following video we can look at the bit sets.
Yeah, it depends on how long time we stay on the transients, of course. Because maybe if we do a live stream, we have some time, and then so it depends. I think I don't think we will stay super long on transients. Who knows?
Okay. Well, I mean, I had a lot of.
We don't need to decide that right now how many videos it is.
Yeah, we just go. Let's just carry on going. I think this is really cool. Next time we do a live stream, I think we can post a schedule for it instead of just like having it there, so that we'll have the link before and everything can be ready. Yeah, Felix says he'd like to see us.
This was the first time we did it. No.
Yeah, this was our first stream. There were a few issues. Hopefully it'll go more smooth next time. But yeah, this was really fun. Yes. And I'll catch you next week, Peter.
Yeah, I enjoyed it a lot. Thank you, Daniel.
Cheers.
Next week.
Next week.